We're looking at combustion analysis. You should already be able to identify combustion reactions, identify hydrocarbons, not name them, just see that they are hydrogen and carbon, and use dimensional analysis to convert between units. But by the end of the video, you should be able to find the hydrocarbons formula when it's burned during combustion. The question in the video is another way to identify an organic substance's composition is to burn it and analyze the products of the reaction. After combustion with excess oxygen, 12 grams of petroleum compound produced 38 grams of carbon dioxide and 18.75 grams of water. And a previous analysis determined that the compound does not contain oxygen, so it's just a hydrocarbon. We want to know what that formula is. So in order to understand this, we need to talk about what these terms mean. Organic molecules have to have the carbon elements. Hydrocarbons have to have carbon and hydrogen only. Therefore, hydrocarbons are organic because they have carbon, but not all organic are hydrocarbons. They could also have oxygen in them. So CH4 is both. CCl4 is just organic. O2 is neither. So just to give you an idea of that. Organic molecules are found in fossil fuels, plants, and animals, and examples are gasoline, oil, kerosene, butane, propane, etc. So when we take those things that are pretty flammable, you can burn them in the presence of oxygen or else it won't burn. And it will always form CO2 and water. So the example of that is taking methane gas that are like cow farts or what's in our Bunsen burners and mix that with oxygen that's found in the air and it forms CO2 and water. There's additional combustion reactions. That was just methane, but if you had ethane or propane, notice they always have oxygen reacting to form CO2 and water, but that also the subscript of the C in the hydrocarbon matches the coefficient of the carbon dioxide. And the subscript of the hydrogen in the hydrocarbon is twice the coefficient of the H2O because you have 2 times that number. So you can use that to help you balance equations and also in order to figure out what the formula was, right? If you know how much CO2 you have, it's directly related to how much C was originally in the compound. So you're not getting carbon from anywhere else. And if you know how much water you combusted to form, you can relate that directly to how many hydrogens were in the hydrocarbon because you're not getting the hydrogens from anywhere else. And that's essentially what we're going to do. So here's an example. The molecular formula of hydrocarbons be determined analyzing the combustion products and their properties. So the hydrocarbon burns and it makes 7.2 grams of water and 17.6 grams of CO2 at standard conditions. And they want to know what is the empirical formula of the hydrocarbon. What was it? How many C's and H's? So what we're going to do is very similar to empirical formulas. We're going to take the 7.2 grams of hydrogen. We're going to divide it by 18.016 grams so we can figure out how many moles we have. See how that's like empirical? You always go to moles first. But then we're going to say we don't want to know how much water we have. We want to know how many hydrogens are there. So for every 1 water, which is in my denominator, I get 2 hydrogens, right? So I'm going to double it for how many hydrogens there are, and there are 0.8 moles of hydrogens. We're going to do the same thing for now carbon. So from carbon dioxide, we know it was 17.6 grams of carbon dioxide, and that 17.6 divided by 44, the molar mass, is 0.4 moles of CO2. And then for every CO2, you get 1 C because there's 1 C in that CO2. So you didn't really have to do much there. You're going to keep the same number. What we can now see is that 0.4 carbons is equivalent to 0.8 hydrogens. So the hydrogens are twice the amount of carbons. So our empirical formula is CH2. For every 1 C, there are 2 H's. Using that empirical formula of CH2, the molar mass is 42, write the balanced combustion reaction. So again, what we do is take the empirical formula and say its molar mass was 14. If the molar mass they're talking about is 42, that was 3 times the mass that we thought. So that means we distribute the 3 through, this is what we did in the last video, and find out the formula was C3H6. Now we should be able to write a combustion reaction, which means we're going to burn it in oxygen to form CO2 and water. And then we're going to balance it. For every 3 carbons on the left, we need 3 carbons on the right. For every 6 hydrogens on the left, we need 3 times 2 or 6 hydrogens on the right. On the right now, we have 6 oxygens from the CO2 and 3 more from the water, so we have 9 oxygens. You can't put a 9 in that next blank because that would make 18. So we're going to write 9 halves. What that means is it's equivalent to 4.5. 4.5 times 2 is 9. But we don't usually write decimal places because it looks kind of strange in the formula. It gets confusing. So instead, we write 9 halves and the 2 cancels with the little 2 in the oxygen formula. And if you want to, you can always put a 1 in the blank box. So back to that question in the video, we're going to actually calculate it now. So we're going to take that 38.96 grams of carbon dioxide, divide by carbon dioxide's molar mass and then multiply by the fact that there's only one carbon for every CO2. So whatever your CO2 is, you get that carbon. But you want to show the grader of your question that you knew that by showing that mole ratio. So we get 0.867867. So that's the moles of carbon. And now we're going to do the same thing for water. So water was 18.752 divided by the 18 on the reference table times 2. So this is the reason why we have to show the original mole ratio of CO2 to C, because sometimes it's 1 to 1, but in this case it was 1 to 2. So you're showing that you know there's twice as many hydrogens in water than there are carbons in carbon dioxide. And so now we have a ratio of how many C's and H's there are, but we want to reduce it by dividing by the lowest number. So we divide them both by 0.86787, and we get 2.3996 moles of H for every mole of carbon. That didn't quite help us much, because our formula would look like C1 H2.3996 or 2.4. So we don't round around that because it's too much rounding to do. What we want to do is figure out what can we multiply this by in order to make it whole numbers. So if I multiply by 2, I'll get something like 4.6 or 8. If I multiply by 3, I'll get something like 7.2. And if I multiply by 4, I'm getting something like 9.6 or something. Finally, when you multiply by 5, you get something really close to a whole number, 11.998. So I'm thinking 5 is my good golden number. It would give me about 12 moles of hydrogen. If I multiply the hydrogen by 5, I have to multiply the carbon by 5. So C5H12, which we know from last year is pentane. At this point, you should be able to find the formula of hydrocarbons using combustion equations.